So thank you for accepting the invitation to give the colloquium for October. I think this is the first colloquium for this semester, and I'm very happy that Nikos is with us today. I will say a few words about Nikos since Vasilis is not possible to attend this seminar today. Nicolas Prantzos is a research director in CNRS in France. He lives in Paris for almost 35 years. He has done theoretical work in the fields of nuclear astrophysics, stellar evolution, high-energy astronomy, and galaxy evolution. And more recently, he has been interested in questions related to astrobiology, like the issue of the so-called galactic habitable zone and the implications of the Drake equation and the Fermi paradox. He has published around 300 research papers with over 120 in refereed journals, and being first author in more than half of them. He has invited review papers in physics reports and reviews of modern physics, about 8,000 citations and an H index of 50. He has also co-edited 2 monographs. The one was published by Springer in 2010, and there has been another edition in 2018 under the title Astronomy Radioactivities. And the second book called Oxygen in the Universe by EDP Sciences in 2012. Apart of this, Nikos has spent a sizable fraction of his time for the popularization of astronomy through public lectures, TV and radio broadcasts in France and Greece, as well as in BBC. And he has written 4 books so far for popularization. They have been translated in several languages, including Greek, and also articles in newspapers, reviews, and journals. We're particularly happy that Nikos is today with us. Nikos is a distinguished scientist of the Greek diaspora. So today he would talk about recent results on the chemical evolution of the Milky Way. And the floor is for you now, Nikos. Thank you very much.
Okay, thank you, Yorgos, for the presentation. Kalispera se olus. Good evening to everyone. I thank the Hellenic Astronomical Society for this invitation. I am happy to be with you over a distance of almost 2,000 kilometers. I am aware that a few months ago, our colleague Despina Hadjidimitriou presented an exquisite review of the latest data release of Gaia, data release number 3 on the Milky Way. And I know there will be some overlap with what I'm going to say, but I'm not going to reproduce that. It is very, very well done by Despina. What I'm going to do is, in the first part, since I know that not everyone is working on such matters, I mean nucleosynthesis, galactic chemical evolution, the first thing is to put all that in context, to recall a little bit how our ideas about the chemical evolution and the formation of our galaxy evolved over time. Then to show how problems arise, mainly through observations during all those years, and how in the last 20 years or so, our progress in understanding all those matters exploded, essentially, thanks due to observations, mostly from larger scale surveys. Okay, so let us start going back to chemical evolution. In the mid-40s, there were basically 2 ideas about the origin of chemical elements in the universe. We have seen already that most of the stars around the sun have a similar chemical composition, like the sun. Mostly hydrogen and helium have a few percent of heavier elements called metals. George Gamow believed that all those elements were made in the Big Bang, in the hot early universe. Fred Hoyle was saying that these elements were made inside stars. As usual, observations revealed in the early 50s that stars that belong to the galactic halo, population 2, but close to the sun still, may have much less heavy elements than the stars of the disk, which are called population 1. And this showed clearly that the chemical composition of the Milky Way is not uniform, so it was impossible that Gamow is right. Hoyle was right, and the more so since at the same time it was discovered by Merrill in S stars that short-lived elements like technetium, which lives for 1 million years, which is nothing compared to the scales of chemical evolution, exist in the abundances of in the surface of S stars, implying clearly that metals are still produced in the present-day universe by stars. Now, to come back to the formation of the galaxy, in 1962, an influential paper was published by Eggen, Lindenberg, and Sandage, which on the title you see there in capital letters. And what they found by looking at stars of various metallicities, content in metals in the solar neighborhood, they used the so-called ultraviolet excess, what you see there as delta of U minus B. Ultraviolet excess, the bigger it is, the more blue is the star. So bluer stars had smaller metallicity. We know that. The reason is, of course, that they have less metals in their atmospheres, so it's easier for the light to filter through the atmosphere, and you can see more deep layers, which are, of course, hotter and then bluer. So they discovered that the color of the stars was somehow related to two things. On the left, you see the eccentricities of their orbits, and on the right, the vertical velocity with respect to the plane. And it turned out that the bluer was the star, so the smaller its metallicity, the higher the eccentricity, and the higher the velocity. And thus, the maximum distance from the galactic plane you see on the very, very right axis, up to 8 or 9,000 parsec, 9 kiloparsec. And here I have put the conclusions, not because no, I'm not going to read all that, but I really like this conclusion because it is stated in a crystal clear way the scenario they proposed, namely the collapse, the uniform collapse of the galaxy. As the galaxy was collapsing from the protogalactic cloud, stars were slowly formed, and they enriched progressively the gas with metals. And so in the end, in the disk, the gas was very much enriched in contrast with the older stars, which were at more eccentric velocities and at higher altitudes. This is what we call a monolithic collapse scenario for the formation of the Milky Way, and it was the standard paradigm, a very influential paper for many years, until it was challenged by Searle and Zinn in '78, which they looked a little bit further than Eggen, Lindbergh, and Sandage. Remember, they had looked up to a few kiloparsecs. Now, as you can see on the right, there is, as a function of the distance from the galaxy, starting from 10 up to 30 kiloparsecs, they observed globular clusters, which are seen much further away. And they found no relationship between the metallicity in this axis, the amount in some logarithmic scale. 0 here is solar, -1, 1/10 solar, and -2, 100 solar. And they showed that basically there's no relation, in contrast to what Engel, Lindenberg, and Sandage had found. So if we look further away, there is no such relationship. And on the right, they also made the metallicity distribution, the number of such globular clusters as a function of their metallicity, here in a linear scale, not logarithmic, as a function, again, of solar metallicity. And they found that this distribution, the observed one, is this solid curve down here, is very, very different from what would be expected by a simple model, this dotted curve here. And the two intermediate curves that you see here are their own model, assuming that there was not a monolithic collapse, but an ensemble of protogalactic fragments that were put together to form the early galaxy, at least, before the collapse to the disk was made. So they put in challenge the monolithic collapse scenario. Undoubtedly, this was influenced by the ideas promoted in those days, mainly by Jim Peebles in the United States, about the bottom-up scenario of galaxy formation, and which was championed by the paper of Simon White and Martin Rees on hierarchical galaxy formation, written again also in 1978. Also, at about the same period, a little bit later, Gilman and Wright, by counting stars vertically to the plane of the disk, to the south galactic pole, they found that the distribution, the density distribution of stars is not a monotonic exponentially declining function, but it can be fit with two exponentials corresponding to the so-called thin disk with a scale height of 300 parsecs and the thick disk with a scale height of 1,000 parsecs. And this again was not something that could be understood in the framework of the monolithic collapse scenario. Especially Alan Sandage, who was one of the greatest astronomers of the 20th century, was opposed to both those papers. But as we shall see, the reality today is, I mean, it's not exactly what Egan, Lindbergh, and Sandage had proposed. So let's come back to chemical evolution now and nucleosynthesis. We have now, since all those years, especially after the efforts of Fowler and of Fred Hoyle, who expanded the theory of stellar nucleosynthesis, we have a rather good picture of how elements are produced from the primordial gas, which is enriched in those elements. Massive and small stars are created and living in different time scales, mega years and giga years. They evolve, and in the end of their lives, they expand the products of their nucleosynthesis either through the winds of planetary nebula or through the explosions of core collapse supernova. And they leave behind either white dwarfs or neutron stars and black holes. In the case you have binary systems now, if you have a white dwarf and a companion star, it may, under some conditions, explode and produce most of the iron in the universe. This is iron group elements. While if you have two neutron stars, they may merge and produce mostly of the so-called R elements, a class of elements heavier than iron and which are very neutron rich. And all this material is injected in the interstellar medium, where it is bombarded by cosmic rays, and so the carbon, nitrogen, oxygen nuclei are broken up and to form lithium, beryllium, boron. And from this material, which is mixed, new generations of stars are formed, and this goes up again. Okay, this is the cycle schematically illustrated here. All this can be put in equations, and these equations require a lot of ingredients, above all, ingredients from our stellar evolution colleagues, stellar evolution and nucleosynthesis. And those stellar properties is the lifetimes of stars. All of these are functions of mass, stellar mass, and metallicity, the yields, the masses of the residues, and the rates of binary collisions, type 1As or neutron star mergers. And you see on the right, as a function of the mass of the star, their lifetimes. Of course, the low mass stars live more than 10 billion years. These stars do nothing for galactic chemical evolution. They do not contribute to it, but they are passive tracers of it. In their surfaces, they keep whatever happens in their interiors. In their surfaces, they keep the composition of the gas from which they were formed. So if we look at a star 10 billion years old, we know that its surface, we see the composition of the gas as it was 10 billion years old. And this allows us to do the so-called galactic archaeology. Now, the other stars, the massive and intermediate masses, live for shorter time scales. They have time to evolve and die, and then they produce what we saw before. They are active agents of galactic chemical evolution. We need also other things, collective stellar properties, the star formation rate, the initial mass function. All those things are provided mostly. We do not have a theory for that, unfortunately. We have phenomenological receipts they produce in the models and also observations and some theoretical arguments. They concern the behavior of matter in scales of tens of hundreds of parsecs. And finally, we need also gas flows, how much material goes into the galaxy or how much material goes outside it or inside the galaxy. And this, again, it's hard to have a theory. We're relying again on observations and on much larger time scales. Now, what we can do for that, and for many years, simple one-zone models of the evolution were made. And of course, they were tailored for the solar neighborhood, because obviously we have many more observations for the solar neighborhood than for other regions of the galaxy or of extragalactic regions. And this would be considered as a first approximation of galactic chemical evolution. Here we have one such model that I did many, many years ago. And you see what we can do with such simple models, which are meant to reproduce what we see in those so-called solar cylinder, namely a region at 8 kiloparsec from the sun, which includes stars also of the galactic halo. We reproduce present-day observables. You see on the right the total mass of stars, gas, the star formation rate, and so on. And on the bottom, the age metallicity relationship that you see there. Such models now help as I would say, a first-order approximation. Essentially, they allow us to test the stellar yields, the overall behavior of the stellar yields, because an important ingredient is the yields of stars. What element comes out of a star in what proportion from a star of a given mass and metallicity. And when we put all of this in the chemical evolution blender and compare with the solar composition, because this is our benchmark, the solar composition, which is well measured, we see that within a factor of 2, you see up there, compared to the solar abundances for the various elements up to the iron peak, within a factor of 2, this is an old model, okay, we perhaps a little bit better than a factor of 2, we reproduce most of the elements, the iron group, this group here, and so on. And this also the isotopes. You can say that perhaps you may think that this is not a very impressive test. However, you should remind that this is relative to the solar abundances. But if we put it in an absolute scale, the solar abundances among the various elements that you see here vary widely. The most abundant metal, oxygen, is 5 orders of magnitude more abundant than fluorine, which is the next to it. There are 5 orders of magnitude. The fact that we are models, this is the red curve, we can reproduce the observations within a factor of 2 is 0.3 dex, and usually less. It's a fairly impressive achievement, one of the triumphs of nuclear astrophysics and our theory of stellar evolution in the 20th century. And this is why Willy Fowler, who championed the measurement of nuclear reaction rates, got the Physics Nobel in 1983. Although many people thought that it was a scandal that Fred Hoyle, the father of nucleosynthesis, didn't get it for some political reasons. Now, an important thing to know, since now we have to enter a little bit more the chemical evolution, is that obviously metal abundances and gas increase monotonically with time. So in principle, it would be nice if we could check our models by observing stars in various ages. But stellar ages are difficult to evaluate. So we use something which is a proxy for age. In that case, what we call metallicity is the abundance of iron. Why iron? It could be any metal, but iron is abundant, it has a lot of strong lines, easily observable. The other thing is that elements, of course, their abundance increase with time, but not in lockstep, all the elements. If you see some element which is 10 times less abundant than in the sun, it doesn't mean that another element should be also 10 times less abundant than the sun. In order of magnitude, it would be the case, but it's not exactly the case. You could see factors of 2 or 3, or even more in some cases. And this is because the elements are not produced exactly in the same type of sites. They have different sources which evolve on different light times, and these sources enter the galactic scene at different periods. And also they have other properties which create abundance patterns, as we call them. And it is precisely the study of those abundance patterns, which is not an exact science, that provides us a lot of information, as we shall see with various examples about the galactic archaeology. Here I have some examples. I wouldn't like to spend a lot of time there. There is one basic consideration about primary versus secondary elements. Primary elements are those that are produced by a given site with always the same amount, independently of the initial metallicity of the gas from which the site was formed. And secondary elements are those that are produced by the metals that entered the star. And their evolution is different. You see here in a logarithmic scale with time, primary elements has a different slope than the evolution of the abundance of a secondary element. But what we measure usually is the ratio of two elements. So let's go to the bottom here. The abundance ratio of two primary elements is more or less constant with time or with metallicity, because we said that we use metallicity as a proxy for time. And the ratio of a secondary to a primary element increases with metallicity. This is the basic thing we have here. This notation that we shall see quite often is a logarithmic notation. Is the abundance ratio of two elements with the abundance ratio in the sun, and we take the logarithm of it. 0, always in this scale, is solar abundance or solar ratio, -1, 1/10, 100th, and so on. And I don't wish here to present an exhaustive think of what kind of patterns we expect. The most well-known one, the one we shall spend most of time on it, is the ratio of alpha elements. By the alpha elements, we mean elements which have a number of 4. The number of particles in their nucleus is a multiple of 4, like the nucleus of helium, the alpha particle, which has 4 particles, 2 neutrons and 2 protons. And such elements are oxygen 16, silicon 28, calcium 40, and so on. So for those elements, if we plot the ratio of an alpha element over iron, we expect to see this kind of pattern, because early on, these elements are produced exclusively by massive stars, which explode as core collapse supernova type 2. And later on, we see also type 1a supernova, which explode after much longer time scales and produce iron. And so the introduction of iron by those type 1a supernova make the alpha over iron to go down. And this is a typical pattern that we shall discuss many times in what follows. Okay, so the abundance patterns play a very important role in our understanding of galactic archaeology, and they allow us to test the validity of the stellar yields, the initial mass function, what sources produce which element, and the overall galactic chemical evolution model. A few things about the yields before. We know a lot about the workings of stars. See, still there are a lot of uncertainties yet, various effects that we know they operate in stars, but we don't know how exactly to model them. And there was also a lot of progress in 2000 when people introduced mass loss and rotation in the stellar evolution models. These are ingredients we know they exist in stars observationally, but it is hard to check what they are doing in the inner workings of stars. And the models there we have for now, they are largely parametrized, of course, parametrized with calibration on observations, but still we don't have a clear physical understanding of what was happened. And there are several interesting things what are done, but I don't have time to go to that. But the bottom line, that those effects, which are very important, affect mostly the outer regions of the star, the envelope, the hydrogen core, even the helium core, but not so much inside. The inner layers, which produce the heavier elements, are basically little affected by those things, perhaps a little bit more by rotation. Rotation is always an important ingredient. But the mixing it produces concerns mostly the product, the amount of products in the mostly in the outer layers. For the inner layers, the important thing, and not well understood yet, is the explosion mechanism. The details of it also play an important role in determining the yields of the elements. Okay, so this is to keep in mind that still for the yields, there are important uncertainties. Now, a couple of years ago, we tried to put together the most recent sets of yields by our colleagues from Roma. Here you see, I don't expect to go through all that. The orange curves is what are with the rotational models, the green curves with the non-rotating models. You see that in some cases, these red cases, there are important differences for nitrogen, for fluorine. In other cases, not so much, but still sizable differences. You see that for all those things in color there is nice agreement with the observations in general, but there are other elements for which we still have no agreement. So this illustrates well the current status of the stellar yields. Depending on the element, we have good answers for some classes of elements, not so good answers for some others. Okay, so let us now see what happens with happened with the observations that we had in the early 2000 or late 2000 up to 2010. We knew that our models could not be considered as representative of what happened. The very simple models I showed you were not representative. Why? Because in the solar neighborhood, you see the age metallicity relationship, you see in the bottom left today, there is very little dispersion. When we observe young stars in the solar neighborhood, they have very little metallicity dispersion, but the age metallicity relation have a very high one. And it could not come from the young stars or the when they are formed or from the gas. This shows that the gas is completely mixed locally. Why shouldn't it be mixed in the past? And the other thing is that when you look at the metallicity distribution, the number of stars as the metallicity here, 0 is solar, you see that in principle, in the simple model, we expect younger stars to have higher metallicities. But here you see, of course, we said ages are very crudely estimated, but still the old stars, the red curve here, go up to very high metallicities and also very low ones, whether the young ones don't go to very high metallicities. And this cannot be explained in this framework of the simple model. And finally, another thing, the existence of the thick disk that we mentioned before in the solar neighborhood. We started knowing a little bit better its properties as a function of all these panels are a function of metallicity. We know that the thick disk is on average older than 9 or 10 gigayears than the thin disk, which is here. It is also on average, its stars are on higher orbits than the thin disk, and especially, this was a very strange feature. There was no continuation in the evolution of the alpha over iron ratio of other elementary ratios, a function of metallicity here. The thick disk developed this sequence, and the thin disk, this kind of sequence here. There were two parallel sequences of the old stars and the younger stars. So how, and there was some distinction between them, kind of a gap between them in the number of stars. And this was very hard to explain. So this was the situation, basically, with the thin and the thick disk. One more thing we knew was that there is a negative metallicity gradient in the disk concerning mostly the gas and young stars. For the old stars, it's very hard to look and very far away from the sun. And this was explained, there were more metal-rich stars in the inner disk than the outer one. And this was interpreted in terms of the inside disk formation. The inner disk evolved more rapidly than the outer disk for various reasons. These are the problems I just mentioned for the solar neighborhood, and these are the problems, especially the chemistry, the Doppler alpha behavior in the thin disk. So, a landmark paper was published in the early 2000s by Selwood and Binney, who opened the way for a lot of revision of our ideas about those models. They discovered that stars inside corotation with the spiral, because the galaxy has a spiral pattern, and these spirals, we know they are transient. So it turns out that if you have a star which is orbiting the galaxy, and it happens to be in corotation with a spiral pattern, one of those spirals, then it is a kind of trapped in this corotation, in the potential wave on this gravitational of this inhomogeneity of the potential well. And it can surf on this spiral wave and be deposited further away when the spiral pattern dissolves. It can be deposited further away from its place of birth. And you see here a toy model that Selwood and Binney produced. Within these vertical curves, stars are formed, and in the end of the simulation, they are found to be within this shaded histogram. And depending on their formation place, this is the inner galaxy, this is the outer galaxy, the distribution is different, and it depends on this kind of spiral pattern. And this has a profound theoretical reason, which was went unnoticed until then. And by playing with that, a very elementary toy model, Selwyn and Binet could show that this high dispersion that was observed could be explained by such a toy model. Around, if there were no dispersion, this kind of things, if all the stars were remaining in their place of birth, we should observe only this curve here. And this is clearly not the case. Okay, so radial migration offered an important new ingredient that we should take into account. And in the late 2010, numerical models, hydrodynamical, I like a lot the title of this talk of Roscar et al., Riding the Spiral Wave. It really illustrates very nicely what's happening, because you can imagine people, surfers in Hawaii, being caught by a spiral wave. They are deposited, they are running along with the spiral, and they are deposited some point, more or less in a line out close to the beach. If the same surfers, you leave them just between the waves in general, after some time, they will be completely dispersed around. The spiral wave puts them, all of them together. And this is illustrates very nicely this picture on what happens when you have this corrotation action of gravitational potential inhomogeneities. And these things were also explored with the semi-analytical models. This was another landmark paper by Hellenic and Binet, because they introduced that in semi-analytical models, not only in riding the spiral wave, but of course in such models we need a kind of parametrization for the radial migration. This is not something we can get from principles. And also with the N-body plus SPH models. And the general conclusion was that indeed the thick disk can be formed by radial migration from the inner disk regions. This is called so-called secular evolution. It does not need something external, some perturbers. But again, if you look more carefully in this diagram, you see the alpha over iron versus metallicity, you see that this color green, which is supposed to reproduce the thick disk, it's colored on the basis not of chemistry. We don't, if there were not colored there, you could not distinguish two sequences. You would distinguish a very thick sequence here with less stars here, but it's normal. The thick disk has less stars than the thin disk, but you would not see a gap between them. And this gap is produced only if you select the stars through age or kinematics. This is what happened here through the kinematics. Okay, to make a very long story short, here is a summary of the ideas in 2010s about the explanation of the thick disk. There were external mechanisms, mergers which were hit in a pre-existing thin disk, accretion of galaxy satellites, gas-rich mergers, and then some internal mechanisms, namely that stars were born hot in an early turbulent phase of clumpy disks. And such kind of things we see in high redshift galaxies also. Or, this is what we saw just previously, they could be produced through radial migration. This is what we call secular evolution. And there were some tests proposed for that. Here you have Sales et al., which used 4 hydrodynamical models at that time. They studied them, and some of them were reproducing nicely the thin and thick disks from the morphology point of view. And they found that what distinguished such models was that most of them, here you have the eccentricity, the number of stars as a function of the eccentricity, most of them, especially the migration model or the merger model, produced small eccentricities, 0.2 here, or the heating model, and the accretion model produced very high eccentricities. And of course, the red histograms are the number of accreted stars, and they are more important. Here, almost all the disk is produced by accreted stars. Okay, now, what changed considerably the game was the introduction of industrial scale observations. Here you see observations by SDSS. In the late 2010s, there are about 205,000 million stars here, extending up to very large distances, 20 kiloparsecs from the 20,000 light years, 6 or 7 kiloparsecs rather from the galactic disk. Most of them belong to the halo. They are colored according to their metallicity. So you see the blue ones in the halo, the oldest modern metal poor stars, and then the youngest ones being down here to the disk. And several other surveys followed with that. The important thing is that these surveys provided us with kinematics, accurate positions and kinematics of those stars, especially Gaia. And here are things that Despina has presented also in her talk. In the phase space of kinematics, the velocity phase space here, you can see colored as a function of the metallicity. Here, the yellow thing is the less metallic stars. Here, the blue is the more metallic stars. So this is the hot thick disk. And then we have seen things that are grouped in the phase space of kinematics. So we think that they belong to groups in the early galaxy. The most important is the so-called Gaia and Celadus group, which has a mass is estimated to a few million solar masses. A few billion solar masses. This is about 310 to the 9 is about 1/10 of the present day baryonic mass of the disk of the Milky Way. But this group is quite old. Its metallicity that you see here, and the abundance ratio is metallicity is very low. And we believe now that it's a merger that happened in the past of the Milky Way about 10 billion years ago. Here is a simulation that has been done after those results. You see, as a function of look-back time, the analysis of a numerical simulation, which has a merger of the size of the Gaia and Celadus merger. And on the one hand, it hits the pre-existing disk. There was a disk before, but it is heated by the collision. And on the other hand, it is heated kinematically, of course. And on the other hand, the gas of this merger, it's a gaseous merger, it contributes to a local starburst. The star formation rate increases during the collision. It is through such kind of observations that we were able to find that in the past of our galaxy, there were such mergers, indeed, along the lines of the scenario of Searle and Zinn, and unlike the scenario of Egan, Lindelben, and Sandage. And now it's time in the last part of my talk to enter a little bit the work we did on those topics with several collaborators. About 10 years ago with Leah Thanasula and graduate student Kubrick, not Stanley Kubrick, Maxim Kubrick, we investigated numerical simulations of a spiral galaxy, which was not a Milky Way type galaxy. It was rather an early type disk galaxy with a strong bar. You see the bar here in the end of the simulation, very, very strong bar. And we analyzed to see the extent of the we analyzed those data to see the extent of radial migration. And here you see as a function of time, here in the top panel, there is the radius of the bar, which becomes longer and longer. It reaches up to 6 kiloparsec in the end of the simulation. The corotation radius, which is outside that. And then you see stars here, these zigzag lines. The blue line, the blue curve, corresponds to the path of a star. The zigzag up, the up-down here, the star is formed around 6 kiloparsecs when in the beginning of the simulation, and it rotates, goes around its birthplace. It's the epicyclic motion, the well-known epicyclic motion. But you see that at some point, after 4 gigayears, it is trapped at corotation, and then it starts migrating outwards. All the time being in corotation, in epicyclic motion, of course. But it migrates slowly outwards, and in the end of the simulation, it's found at 16 kiloparsec, 10 kiloparsec away from its birthplace. Okay, this is just an illustration. There are many stars, many possibilities, and here you see as a function of the final radius, the initial radius of the star, and you see that if there were no radial migration, the stars would lie along the diagonal here, but they are not aligned around the diagonal. And especially in the outer places, there is a lot of radial migration. Stars that are, for instance, here found in their final place at 14 kiloparsec, they are initially produced at about 10 kiloparsec. Okay, this is what tells us. In contrast, the gas, which is dissipative, it's more or less around the diagonal. It cannot travel far away because it dissipates its energy. And so it's around the diagonal, and here is the corotation radius. Now, by analyzing those data, we could see how far away the stars were going with respect to their birthplace. So stars which are found, which are at 8 kiloparsec, they were away from their place of birth by this delta R. And you see that in the beginning, after 2 gigayears, they were rather closely to their birthplace, but as time went by, they were more and more further away. And we could numerically approximate this with functions, with coefficients depending on time and radius. It's like a diffusion process, as was also discussed by Brunetti et al. And so we presented the model, a semi-analytical model with all those things. I don't have to go through. I will present rapidly these older results. Whatever you see there with curves, red curves, is the situation of the galaxy as a function of radius at 4, 8, and 12 gigayear, the thickest curve. And the thickest curve should be compared to the observations, which are the shaded areas here for the gas fraction, for the abundances, the negative abundance gradient for oxygen of iron that we see there, and for several other things. The important thing, which plays a big role in that, and what I shall discuss now, is the infall time scale. The galaxy is made from gas that falls inside out, so very rapidly in the inner galaxy in a couple of gigayears time scale, and much more slowly in the outer galaxy at almost 10 gigayears time scale. And this plays an important role for the abundance gradients, but also for what I will show in a moment. Now, here I make a jump to more recent work. See, this is paper we are going to submit soon. And I compare here with data of the DR3 release of Gaia. This is part of what Despina presented in her talk. Here is the gradient of open clusters as a function of distance from the galactic center, gradient of metallicity, negative, gradient in alpha over iron, which goes the opposite way. And here is the same thing. It's these mean here, right? Thing is the gray curves here in those figures. And these colored curve is our results, shaded by 1 and 2 sigma dispersion correspondingly. We have a small offset here by 0.1 dex here or here, which is understandable in view of the uncertainties on the stellar yields. But overall, it's not a bad agreement. What counts here is the slope more than the absolute value, and it's okay. And here is the evolution of the metallistic gradient with the data as a function of age. And this is our model essentially. So it's an acceptable model. Now, what does this model do for other things? Okay, I will go rapidly through that. In the mid panel, this is important to notice also. As a function of the radius, the birth radius, we take the stars that are now found at 3 places. 8 kiloparsec is the position of the sun. So this histogram here, the red histogram, shows the birthplace of the stars that we find now around us. And you see that most of those stars are made in the inner regions at 3 kiloparsec. And they are found today because of they are scattered essentially today in the solar neighborhood. Now, this is the old stars. The young stars, those correspond to the thin disk, a large fraction is made locally at 8 kiloparsec, but we also have stars that have been produced in the inner galaxy. Okay, this gives also something like what we saw before. Yeah, the numerical simulations we analyzed. So here you see again the final radius versus the birth radius. Diagonal is if there were no migration at all. The blue curve corresponds to the thin disk, the relatively young stars, younger than 9 gigayears. And we see that the stars of the thin disk that we see today at 8 kiloparsec, they were mostly, on average, made at 6.5 kiloparsec. This is their birth radius. And this, of course, raises the question, what about our own sun? Was the sun formed inwards, not in the place where it is found today, but a couple of kiloparsec inwards? This is a very important fundamental question because, as I explained since the beginning, whatever we are doing with these abundance patterns, we always compare, we have as a benchmark the sun and the solar composition because it's the best known composition. And if we change a little bit the place of the sun in our scheme of thinking, then it changes a lot of things, in fact. As for the thick disk at 8 kiloparsec, we see that on average it is formed inwards. So it's at 4 kiloparsec. The stars of the thick disk are formed mainly inwards. Now, how does this translate in terms of observations? Here I'm trying to be as pedagogical as possible, and because in most cases, when we see, there have been dozens of models published on the thick disk, especially in the last 10 years. And it's not always easy to understand the patterns there that they are produced. So here, what you see in the top panel as a function of the age is what happens in the gas in each one of in every two zones of the model. So the red curves are for the inner zones, inner to 4 kiloparsec. The blue curves are intermediate zones, the green curves outer zones. Now, the solar neighborhood in that would be at 8 kiloparsec. This is the dotted curve here. The thick portions of the curve correspond to the periods where the star formation rate was higher than the average, and the thin periods when it was lower. So you see that the inner regions were active in the first part of the evolution, the oldest times here. Then, because the disk is formed inside out, then the intermediate regions, then the outer regions. And you see that the gas in the solar neighborhood had a metallicity lower than solar when the sun was formed. It was not solar, the metallicity. It is solar today, as we observe indeed. So how it happens that the sun is here? When the sun is here, because it obviously in this scheme migrated from the inner galaxy, from the zone at 6 kiloparsec, not at 8, but this is 6 kiloparsec, the zone at 6 kiloparsec. And here we see, this is something which is related to that. The bottom panel is related to the top panel. It is what we would observe today when we look at stars of various ages. We look at essentially in all those regions, but we see a mixture of stars that have migrated up to the solar neighborhood. So we see those two big blobs, which is the majority of stars, and they underline the thick disk and the thin disk, and we see a lot of dispersion around, as observed. And also, instead of having this relationship here for the solar neighborhood, we have something which is flatter now. What about the age metallistic relation? This is the same metallicity. I will go a little bit faster now because I'm running out of time. The reason I'm showing this is the same thing as the previous relationship, but now I put metallicity in this axis and age in this axis. The curves have the same, it's another way to present things. And I present things differently because I want to show this blue solid curve here is our results. It tells us that as metallicity increases, for most of the time until we reach solar metallicity, the average age of stars goes down, decreases. Stars that we observe around us are younger and younger. And that is understandable. This is a normal state of things. As time goes by, metallicity increases and the stars are made more and more recently. That's fine. But then you see that as we go to even higher metallicities, the age increases again. And the reason for that is that all these stars now at higher metallicities, they are not formed locally. They come from other regions. Those stars are not these ones here. They are stars that come from other regions that have traveled through radial migration until our solar cylinder. And of course, it takes time for this travel. On average, radial migration takes about 1 billion years for 1 kiloparsec. This is an average, of course. Some stars can travel much faster. It depends on the way they will be trapped in the corrotation. And the blue curve is our results. And the purple curve here, you see, are observations that were made by Fayet et al. This blue curve was proposed already in the Kubrick 2015 paper. This was a prediction of the model, and this is more or less close to the observations. Okay, this illustrates some other aspects of radial migration that I don't have time to go through. So let me come to the important thing, because we are discussing about patterns. So the alpha over iron, this is again the top panel, what happens in the various radii of the model in the gas. And in the bottom panel, you see what we should see locally in the solar neighborhood. And you see appearing clearly the two almost parallel sequences, the thick disk up there and the thin disk down here. And it is because for this part, we see mostly things that were transferred here from the inner disk. And here we see things that are mostly made locally, except this region here, the super rich metallicity region, where we know again that stars are brought here from the inner disk. Okay, these things correspond to, up to now we discussed this alpha over iron pattern, and this is reproduced because we have two types of elements. Alpha elements, as we said before, like silicon, they are produced by massive stars which evolve in short time scales, and then iron in the denominator, which is produced by long-lived stars. This is the main difference of the two. Because we mix locally two populations of stars that are produced in different regimes. The inner disk, which evolved very rapidly, and the region of where we are now, which evolved on longer time scales. This is the important difference. But what about other elements? Now, if we are interested in other elements, we see that the important thing for the patterns is the time scale of the source. We just discussed that, short-lived versus long-lived sources, and then its production at primary or secondary. So we have two variables, and each one of them can take two values. On total, we have 4 combinations for an element X in the denominator, and also for an element in the denominator. So if we plot the two of them, then we have 16 combinations, and you can see them there. But it's better to see them in this scheme, which illustrates from the paper we are going to submit. In that thing, you can discuss elements this in the blue patterns that are produced on similar time scales and as primaries, so from the same source, silicon or magnesium. We expect to have something which is not a two sequences, but one single sequence with a slope 0, because they are going lockstep. They evolve in lockstep. This is also true for nickel and iron. These are iron group elements. They are produced mostly by type 1a supernova, so it evolves in the same way. So it's the ratio does not evolve with time. And then we see also other type. These are S elements. And in other cases, okay, this is there are some other cases, but I don't have to discuss them there. What I want to point out is that this thing, the fact that we see 1 or 2 sequences in the thin and thick disks, can tell us a lot about nucleosynthesis. And why is it important to see in this region? Because this region is between 1/10 solar and a little bit more than solar here in metallicity. Such environments exist today around us. The small Magellanic Cloud has a metallicity almost 1/10 solar. And there are regions which are a little bit supersolar. This means that we can test our model stars, the massive stars that we need, in such conditions. We can look for stars in the small Magellanic Cloud. We can see if our model stars, how they compare with that. In contrast, it is hopeless to look for stars today that have a metallicity of 100 solar. They don't exist. And so the yields of those stars, the models we have, are totally theoretical for the moment. We cannot calibrate them. That's why I think this kind of results offer us a very nice test of our nucleosynthesis models. And I will finish with, this will be the last part of my talk. I mean, it's a very short part, about some recent work reporting recent star formation episodes in the Milky Way disk. We discussed up to now episodes of star formation that happened in the old disk, many billions of years ago. Now, recently, there were reports, first with Gaia DR2 release by the Besançon group, about a recent large burst in the evolution of the Milky Way. Here is the age. So this burst was supposed to be produced about 2 to 4 giga-years ago, billion years ago. It's more or less at the period where our sun was formed, if we believe in those data. Other reports with different data, the Gaia data, this is the Australian survey, analyzing stars, reported two bursts. You can see them in the metallicity versus age. And these now are 6 billion years ago, before the formation of the sun, or 3 billion years ago. And there are even reports, more recent ones, I think this is, 2022 or 20, for three bursts that you see here. One of them, again, 6 billion years ago, and two weaker ones and more recent. And the claim of those authors is that those coincided with the Perigalacticum passages of the Sagittarius stream, a small galaxy which is supposed was detected about 20 years ago, and it was not seen because it's from the other side of the galaxy with respect to the sun's position. And its Perigalacticum passages could be estimated. So this is the first Perigalacticum passage, almost 6 billion years ago, that you see here. And then, of course, a stream was formed 3 billion years ago. And then 2 billion years ago, a second passage, 1 billion years ago, another passage. And this is the position today. And it is claimed that during those passages, an increase of star formation rate happened. So we tried to model with graduate student Tiangshan Chen. And here are some of the results of our model. We are trying to reproduce this is the one burst or three burst here, and the impact it has on the distribution of metallicity or alpha over iron ratio, where we see overdensities in this plane. And these are things that are in principle observable, and we reveal also the situation if our galaxy undergone recent mergers. So I summarize very rapidly what I tried to say in the last part of my talk here. We are still far away from understanding fully what happened in our galaxy. What is certain is that the observations we have now in industrial scale, and we have even more of them in the forthcoming years, will allow us to reconstruct the history of galaxy to a great precision. For the moment, the picture we have is rather confused. The models we have reproduce some features of the galaxy, not all of them. Some of them are even conflicting between themselves. So the picture is not clear for the moment. And this is always the case after when a lot of observations are available. And I finish with this short movie based on numerical simulations. We show how this is a picture of how a spiral galaxy is formed, and you see in filaments that are created by the condensation of the primordial fluctuations of the gas after the Big Bang. Small galaxies are formed, small proto-galactic fragments, as Cyril and Zinn called them, and they come together little by little, producing a galaxy, a proto-galaxy, spiral galaxy, and producing all those things that now we can see in the phase space of the observations, in the phase space of kinematics, because the position of all those things now, of course, did not remain the same over the years. But thanks to the observations and the wealth of the data we have, and also the chemical abundances at the surface of the stars, we can reconstruct. You see this major merger here, because this is not the whole story. This is a major merger, like Gaia and Celadus that we discussed before. After that, the spiral disk is reconstructed, and now we see that it evolves in a more quiet way. Now secular evolution is fully in place. Of course, we cannot exclude late mergers, but small mergers this time, later some burst episodes. Okay, so this is all for the moment, but it is clear that these are bright times for galactic archaeology and bright times for students to enter this field. Thank you very much for your attention.
So thank you very much for this interesting talk. So now we have time for questions. Please raise your hands and I will see. I don't see any raised hands.
Ah, that's good. That means that it was perfectly clear.
It was perfectly clear, probably.
Can I ask a factual question?
Of course, any kind of question, even not factual.
You didn't tell us much about the initial conditions of the last simulations.
Ah, yes. I have to go. Thank you, Leah, for the question. But this is obviously a cosmological simulation.
Yes, that I can see.
Yes, that you can see. Now, I think it's a Japanese group. Probably you know that better than I do. Now, what's the name of the guys? I'm not very good at that, but I'm sure it's a Japanese group. And the simulation was made, I would say around 2018, 2017 or something like that. I don't show that because I think it's realistic. It could be realistic. I have no idea. But from the aesthetic point of view, it illustrates very nicely what I wanted to say. And that's why I'm showing that.
Okay.
Perhaps things were very different. One thing I would say, I would like to say about that is the following. This is a disk galaxy today, okay?
Mm-hmm.
Now, you see that this is not very homogeneous. It's even from the morphology, there are over densities. We know that in our galaxy, which is also a spiral, the sun is positioned somewhere around here between spiral arms. Now, the question is, what kind of observations? Of course, we have observations around the solar neighborhood. Okay, perhaps in a big volume now with Gaia. But the point is that the simulations give us this picture. So what do we do with the simulations? What kind of volume do we pick up? In the old days, we were picking something which was at 8 kiloparsec from the sun, 8 kiloparsec from the galactic, from the center of the spiral, and we assumed azimuthal radial symmetry, Now, can we do that? Because this position here is also at 8 kiloparsec from the sun. But the picture around is very different from this position here. So which position should we pick up in the simulations? And this is a kind of philosophical, but also practical question. I mean, it's not sufficient to have 3D models with cosmological simulations. The initial conditions play some role, but also the final conditions, how we pick up the volume which we compare to the observational data. This is also interesting.
Well, in this case, it's rather difficult because it doesn't really look like what we expect. The bar is supposed to be for about 5 kiloparsec and the sun around 8 kiloparsec, order of magnitude. And this is definitely not what you see where you pointed. You have to go much further in, and in that place, you're more or less around the ring, which is not what we see in our galaxy. It's a mess.
Yes, but suppose you had exactly what you are saying. Then again, it wouldn't be radially symmetric. You should pick up a place.
Yes, of course.
Yeah. But, sure. So this is what I wanted to point out. Exactly. Okay.
Sorry, Nico, it's Jason here.
Hello.
Just to follow, I had a separate point because at some point you raised an issue about the ion production or the nickel production in type 1As, but I think that's a bit too esoteric for a general question. But in the issue that you were just talking about, if we just look at Andromeda and did an azimuthal averaging, how far wrong would we be to assume that where we are might as well be representative? Is this would we be within your uncertainties for the abundances, or would we be quite far?
I see. I think I see your point, Jason. Okay, we have made models also comparing Andromeda and the disk of the Milky Way, but of course they were not hydrodynamical models or things like that. They were semi-analytical models back in 2009, I think, with colleagues. And we revealed that there is a kind of self-similarity in the abundance patterns and other patterns between disk galaxies, considering their abundance gradients. Andromeda is more metallic than the Milky Way, by the way. It has about 1.5 to 2 times on average more metal rich than the Milky Way. So it's, and also it's bigger. Its disk is bigger than the Milky Way. So the question is, what is the equivalent point than the sun in these conditions? Of course, it's not at 8 kiloparsec, it's further away. And then the next question is, what patterns do we see in Andromeda? We don't see with the same precision as in the Milky Way. We cannot look in Andromeda and see small mass stars and do galactic archaeology for the moment. We see only the brighter stars. But of course, with the bigger and bigger telescopes, like the ones you are constructing at ESO, I hope that at some point we shall see also main sequence, the dwarf stars in Andromeda with ages of several gigayears, and we shall be able to reconstruct this kind of patterns that we reconstruct for the Milky Way. In other terms, to do galactic archaeology also for Andromeda. And then we shall see more clearly in what happens in Andromeda. For the moment, what we know about Andromeda is very, very limited. There are some similarities. Of course, there is a negative gradient of metallicity pointing to an inside-out formation. We also know for Andromeda that it suffered a major collision a few billion years ago. This was showed by several people about 10, 20, 12 years ago. We know several things, but we have not the same knowledge of the chemical patterns in Andromeda as for the Milky Way.
Thank you. On the iron, it was just a question that you seem to be referencing at some point the yields from W7. So I was a bit confused about that, but I think that's just
okay, you are right. You are right. Sometimes, it's hard to make something which is a presentation addressed to all public. Some of those things I recognize that they are addressed to. They have been made for other public. I mean, for people more knowledgeable about that. Okay, so for type 1a supernova, we have models. And there are some models which are more popular than others because they produce better some of the data. In this case, the abundance pattern of elements. And probably the most popular model is the W7 model of the Japanese group from the 80s, Nomoto and collaborators. But this model, although very successful, it has a problem with nickel. Okay, it produces a little bit more nickel that it should produce. It's not the nickel to iron ratio it produces is not solar as it should be, and we know this. So this is what I have obviously left in the slide you are discussing. I don't remember where it was, but I think if this was your question. This was it this the question?
Yeah, that was the point that I was a bit.
Okay, we are confused because
as you said,
we are not
very
aware of all the intricacies of what we are using. But this is a very big point. We are relying. Yes, this is probably what you say. Yes, this thing here. Yes, because we are relying for all these things to the yields that our colleagues of stellar evolution and nucleosynthesis provide us. And these are just numbers. How can we check whether a star of, say, 20 solar masses produces 1 solar mass of oxygen or 2? The answer is we don't know. All these numbers can come out of models. In very rare cases, in fact, the only case is one you know very well, Jason. is the case of supernova 87A. It's only there that we had the opportunity to know the progenitor of the star, what mass it had, 18 solar masses, something like that, the metallicity of the progenitor, which was the metallicity of the Large Magellanic Cloud, and to see, for some elements, how much material in the form of oxygen with larger bars, as you know, came out. Especially iron. We know how, from the light curve, how much nickel was produced, so how much iron. But that's about all. And this is only one point which serves as calibration for most of the nucleosynthesis yields for massive stars. For type 1a supernova, we have no points to calibrate the models. So we just take the numbers, whatever they are worth for. For me, it's a miracle, a real miracle, the fact that we can, in the end of the day, produce that. It's a real miracle. Of course, it's not a miracle. It is due to the fact that...
Very beautiful physics.
Yes, but it's not a miracle. It simply tells us, because in the nuclear reactions are extremely sensitive to temperature. Stars of various masses and so on have different central temperatures. We are dictated by their mass. Never mind if they have different opacities, different metallicities, it makes a little bit of difference. But to a first order, this is the Addington model. It is the mass of the star that determines the central temperature, whatever you are doing, if it's in hydrostatic equilibrium. This tells us this simple thing, that the central temperature of the star is well estimated. And the nuclear reaction rates as a function of temperature are well known. And this is the triumph for Willy Fowler. Once you have that, to a first order, you are fixed. And then the remaining is the patterns. But this is the first order. Okay, this is the absolute abundances. To a first order, we are okay. We can look for patterns then, difference a factor of 2. Okay, this may come from other differences in the models, whether there was rotation, whether there was mixing, whatever. But this, a Nobel Prize is never given by chance, I mean, or by accident in physics. This is really a triumph for nuclear astrophysics, but also over our understanding of the interiors of stars.
Couldn't agree more. Thank you very, very much. It was a lovely talk.
Yeah, thank you. Okay.
So any other questions? I don't see raised hands, so I don't know if anybody else has a question.
Okay, thank you very much, Ilya.
So thank you again. Thank you very much.